Okay, good morning. I am doing a summary on all the different types of functions today because the homework will be on the functions. Okay, so I have done a few videos where I've looked at functions before. We've looked at how to draw functions of straight lines using various different methods. And now we're going to have a look at some of the identifying features of the different types of functions that we have. Okay, so I want to just share my screen. Okay, there we go. Awesome. So, what we are starting off with is our linear functions. And linear functions are our straight line functions. So we know that our linear function has the basic form y equals mx plus c. There it is. And yeah. And we have been looking at that one in the most detail. So we've been doing the gradient intercept method, the dual intercept method, and we know how to draw those lines. Okay, so let's have a look. When we have our graph y equals mx plus c, our m is our gradient and our c is our y-intercept. So if we had our axes and we had a straight line going through the origin, we said that there would be no c value for that. And we said that would just be equal to y is equal to mx. Okay? Just move my screen. Y is equal to mx. Okay, so there's no plus c because it doesn't have a y-intercept. Okay, but if we had a y-intercept, there would be, let's say, 2, because we can see that both the lines actually look like they have the same gradient. They are parallel. Okay, so this would be y is equal to mx plus 2, because our y-intercept would be 2. Okay, when we look at our domain of our straight line graphs, unless we give it a restricted domain like we practiced in our last videos, our domain is always xer. X is an element of real numbers. And we can undo that. Okay, what we can actually do is we can write xer in sepals notation. So instead of writing xer, we can write from negative infinity to positive infinity. And we put curly brackets there because when we have curved brackets, we mean we're not including it. And when we have square brackets, we mean we are including it. And because we don't actually know what infinity is or negative infinity is, we can't include it. So we have to put curly brackets. Okay. If we look at our range, we see that we say that our range is YER. Because if we look at a straight line, every single value of y is included unless we restrict it. I've explained this before, I'm just going over it again. Then we can also write our range or our y's as the same thing as our x's. We know it's between negative infinity and infinity. Okay, and curly brackets again. Okay, when we have no gradient, so when we have no gradient, our horizontal line, our function will be a horizontal line. Okay, and when we do a gradient, it'll be at a slant. And then when we have a vertical line, we just call it y equals k, where k is a constant. Okay, so k has to be a constant in order for us to know it's a vertical line. So even if it was y equals 2, y equals 3, we'd be able to draw that. So let's quickly draw a horizontal one. So when we have no gradient, let's say we had y is equal to when we have a horizontal line, like I just said, we have y is equal to a constant. I've written this incorrectly. Y is equal to, let's say, 2. So if we have an intercept of 2, that will be our y equals 2 line. Okay, our vertical line is not when y equals k, it's when x is equal to k. So I had that down wrong, okay? So if we had to draw that, we would have our x is equal to 2. Let's have a look. So if we had to look at our x values, 1, 2, that would be our x is equal to 2. These are our y's, these are our x's, y's, x's, y equals 2. Okay. So this is x is equal to 2, and that's y is equal to 2. Okay, so those are our straight line graphs. Let's have a look at our parabolas. So when we're having a look at our parabolas, we see that we have our parabola general form is y equals x squared, okay? So if we remember, our parabola, okay, is going to be a function like that if we have y is equal to x squared. If we have y is equal to negative x squared, we have a parabola that looks like that. Okay, a downward parabola. Okay, if we have a look now at our parabolas again, our domain is xer, because if we have a look at our x values, which are all of these are our x values over here. If we look at our parabola, it's actually going to keep on going and going and going and going and going until it runs out of space, which is never. It keeps going up into infinity on this side, and it keeps going down until infinity on this side. So our range, which is our x's, is xer. Our domain is xer. Sorry, domain is xer because we're looking at our x's. Our range, however, as we can see in each of our functions, they don't continue all the way up or all the way down. They have a point where they stop. Okay, so when we're looking at our range of our positive parabola, our range is from the bottom all the way up until infinity. So if we have a positive parabola, okay, so if y is equal to x squared, our domain is going to be from x equals 0, but in this parabola, our x actually does touch 0. So it goes from 0 up until infinity, but we can't include our infinity. If we have our y is equal to negative x squared, so we have a negative parabola, then our domain obviously our domain is xer, it goes forever, xer, but our range in a positive parabola is that. Okay, sorry. Now if we're looking at our negative parabola and we want the domain, that's also xer, like we discussed. But when we're looking at the range now, that's different. That's going to go from 0 again till negative infinity, but we read from left to right, so it's going to be going from negative infinity to 0, and we can include the 0 because it'll touch the 0. Okay, and because we have this y equals x squared function, whenever we put in a y value, let's say our y value is 1, our x squared is going to be plus 1 and negative 1. Okay, because when you square root it, you get plus minus. Okay, I'm just going over these in general now, and then I'll go over some proper examples tomorrow maybe. Okay, so let's have a look. Our last thing I wanted to talk about was the axis of symmetry. So if we have a look at our original parabolas of y equals x squared, okay, we can see that they actually are symmetrical around that midpoint, and that midpoint in our y equals x squared is always going to be 0. So our axis of symmetry is always at y equals 0. Okay. If we moved our parabola away from that origin, we would get different axis of symmetries, okay, but they're always symmetrical around that point. Let's have a look at our hyperbola. So if we have a look at our hyperbola, we see that our function's general form is y equals 1 over x. Okay, sometimes this is hard to see in the beginning because they will give it to you in this form, xy equals 1, okay? But we can see from there that if we were to just manipulate our equation, we would get y is equal to 1 over x. We just divide by x on one side and we divide by x on the other side. Okay, so it's the same equation, just different forms, so that's why it's sometimes hard to tell. Okay, the domain is all real numbers except x equals 0. Okay, so I need to draw this out for you to show you. Okay. So if this is my asymptotes, or my x and y, we have our y and we have our x's. If we draw our hyperbola, our positive hyperbola looks like this. It's in this quadrant, and it's in this quadrant. Okay, so this is y equals 1 over x. Okay, and this line keeps on going forever in the upwards direction and in the sideways direction, and our bottom one continues as well in that direction and downwards. Okay, so if we were to talk about what's actually happening, as our x values increase towards 0, my y values decrease all the way down to negative infinity. And as my x values pass 0, they're back up at infinity and they come down. And as my x values continue on, they just travel towards 0. Okay, this line never touches, our function never touches our y-axis, and it also never touches our x-axis when it's in this form, y equals x, 1 over x. Okay. So the domain is all real numbers except for x is equal to 0, which makes sense because as we travel along our x-axis, they're all included, except when we get to 0, it's not there. Our lines drop off and go up. And as you go past 0, our function starts up again. Okay, so our domain is all real numbers, XER, but x is not equal to 0. So we can write that in there. That could be written as x is an element of the reals, but x is not equal to 0. Okay, same thing with our y's, with our range. We can have YER, but y is not equal to 0 either. Because as we move along our y's, we can see that there is y values, and as we get towards 0, nothing, and then it starts again. Okay, so we call these lines that our function won't touch, we call them our asymptotes. Okay, so we call these our asymptotes, which are very important. The graph won't touch them, okay? And in our hyperbola, in this form, our asymptotes are at x equals 0 and at y equals 0. Okay, so wherever the graph won't touch a line, that's called an asymptote. Okay, and now we are on our last type of graph, which is called the exponential graph. Okay, and this is always in the form y is equal to k to the x. Okay, so it's not to be confused with x squared. Okay, remember in our parabola we had x squared. Okay, now we have something to the x. Okay, in this exponential. So that k is a constant that is greater than 0 and is not equal to 1. Okay, so that's really important down here. That k is greater than 0 and it's not equal to 1. Okay, when we see this, we can draw a function. And our function, okay, looks like this. And the function y equals k to the x, okay, always, always, always go through the point 0, 1, okay? I'll tell you why now. And then it goes up exponentially. Okay, where we've seen these exponential graphs looking like this before, think about our corona statistics. Starts off nice and low, and as people start infecting each other, it goes up exponentially, because for every one person that's infected, you infect 3 people. So it goes up in 3s every time someone gets infected. So that's why it's exponential. Okay, so let's have a look at why it will always go through 0, 1. Okay, so if we plug into our formula, when k is equal to 0, so let's have a look. When x is equal to 0, okay, so when x is equal to 0, we'll get y is equal to k to the 0. Okay, why is this important? Because of our exponent laws, we know that anything to the 0 is equal to 1. So when x is equal to 0, k has to be equal to 1. Okay, y has to be equal to 1. So we have 0, 1 in our exponential. Okay. Then the greater the value of k, the steeper the graph. Okay, so as k gets bigger, we're going to get a steeper graph. Okay, and so obviously k is allowed to be, because k has to be greater than 0 and not equal to 1, obviously k is allowed to be between 0 and 1. Okay, so if k is between 0 and 1, our graph looks a little bit different. Okay, so if k is between 0, oh, let me erase all of that. Okay, if k is between 0 and, it's not a lot of equal, k is between 0 and 1, this is what it looks like, okay? So we are now going in a negative direction. Okay, again, this graph will keep on going down and down and down, but it will never hit x is equal to 0, okay? Which means we essentially have an asymptote at x equals 0. So x, or y equals 0, sorry. Y equals 0 is an asymptote. Y equals 0 is an asymptote. Okay, because it'll never touch it, and that's what an asymptote is. Okay, so these are my 4 different kinds that I need to know. Okay, I now want to just quickly show you some more, just what happens when we move things around on our graphs. Okay, so I want to share this. Okay, cool. So right now I'm looking at graphs. So we just had a look at some exponential graphs. Okay, I'm going to show you a linear one first. Let's do y is equal to x. Okay, we can see that that is going through our origin exactly like we thought. If we do y is equal to 2x, we are just changing our gradient, okay? What happens if we make that y equals 4x? It's even steeper, okay? Let's see what happens when we do y is equal to x plus 3. Okay, I'm going to take this one away. We can see that my y is equal to x is the same exact gradient as my y is equal to x plus 3, but it goes through 0, 3 on my y-intercept. Okay, so these are some linear equations. Let's see what happens if I make this x negative. We can see it just flips. Okay, so now we have a negative gradient. Okay, but the exact same graphs. Let's have a look at some parabolas now. Okay, let's do y is equal to x squared. Okay, y is equal to x squared. Let's see if my assumption was correct. I said that it keeps on going forever and ever and ever. Okay, so here's my origin, you can see it. It keeps zooming out and out and out and out. This parabola just keeps on going forever and ever and ever. Okay, that's why we can say that when we're talking about our range of our parabola, that it goes from 0 all the way to infinity, because it doesn't ever stop. Okay, so this was a nice parabola. And we can see, because it's a positive parabola, it's a happy smiley face, because there isn't any negatives in it. Let's have a look at a negative parabola. Okay, negative x squared. Ooh. Negative x squared. Okay, negative x squared is the exact same parabola, just upside down, just like I showed you. Okay, if we do x squared plus 1, you can't see that, but it just moves it up 1. Moves up its y-intercept, the exact same way as our linear equations. What if we did x squared, and you can see the intercept ends up being 0, 1, same exact way as our linear. If we do x squared plus 3, we're expecting our intercept to be 0, 3, exactly what it is. Okay, these are parabolas. Let's have a look at our hyperbola now. Okay, so let me exit these. Hyperbola is in the form y equals 1 over x. So let's have a look. Y equals 1 over x. So let's choose an x, 1 over 2. Sorry, 1 over... Let's do y equals 1 over 3x. Come on. No, it's fine. Is this, do you need to be in here? Are you in here now? Okay, why is this not working? Oh, there we go, because I'm not zoomed in enough. So let's zoom into my hyperbola. 1 over 3x. Okay, let me just do 1 over x to begin with. Okay, 1 over x. So you couldn't see it originally because I hadn't zoomed in enough. So we can see we have 2 hyperbolas, and as we go left, it's not touching my x-axis, and as we go right, it's still not touching my x-axis. It gets super close, but it never gets there. We can see that if you pull it, my x's go, my y's will never reach 0. It just keeps going down and down and down and down and down, but it's never going to reach 0, 0. Okay, and then, yeah, this is our hyperbola. What if we do a negative hyperbola? Y equals -1 over x. You can see it's just a reflection. Instead of being in these two quadrants, it's in these two quadrants. Okay, I hope that was the right way around for you. Okay, and then as we change things about it, let's make this 1 over 3x. We can see it gets closer and closer. Let's make it 1 over 30x. It gets closer and closer and closer. These are just things you can play around with. Also, if you go onto this website, desmas.com, you can play with any graphs you want. Okay, and then the last graph type I wanted to do was my exponential. So we had y is equal to, let's do 2 to the x. Okay, so here we have an exponential graph. What do we remember should be our y-intercept? It should be 1, remember? Let's have a look. 0, 1, it is. Okay, let's try another one. Y is equal to 5 to the x. Okay, let's have a look. You can see the purple one is the 5 to the x. It's a completely different graph. It goes up at different points, but we can see that it still goes through at 0, 1. Okay, let's just try one more. Y is equal to 60 to the x. Why not? And as we can see, we have a steeper graph, but it goes through at 0, 1. Okay, now let's have a look at our negative, our ones that are with a k that is between 0 and 1. So we have y is equal to a half to the x. Okay, it is exactly what I thought it would be and what I explained it to be. It is just the inverted one, so it goes the other way, and it still goes through 0, 1. Okay, so nothing changes the point that it goes through. It always goes through 0, 1. Okay, and as you can see, they never go past my y equals 0, horizontal asymptote. Okay, so these are just a couple of different ways of looking at the graphs, and a couple of new facts maybe that you might not have known before. Hopefully you did know most of them. Does anyone have any questions for me before I end? Because I'm done now. Okay, perfect. If no one has any questions, then I am going to say goodbye, and I will see you tomorrow. If you have specific questions, please bring them tomorrow. Okay, bye.